Okay, everyone. In this video, we're going to look at an introduction to bonding in solids, and this is going to focus on the content that's in Chapter 22, and this is sort of a streamlined approach to looking at Chapter 22. If you can kind of grasp some of the basic concepts that's in this introduction to Chapter 22, you'll understand sort of the summation of what we've done in Gen Chem. So thus far, we've talked about bonding in a lot of different things. We've talked about bonding in molecules like CCl4. We've talked about bonding in molecules like H2. We've talked about linear combination of atomic orbitals. That was back in first semester. And we've even talked about bonding in covalent complexes and Lewis acid and base chemistry. In this video, we're going to focus on bonding in solids, where in solids, what kind of distinguishes a solid and makes a solid is that we have the atoms organized into crystal structures. So they're periodic and they're put together like Legos into a periodic organized crystal structure. So what you can see is that we have gold, silicon, and diamond, and these three materials are all solids, but yet have very different physical properties. I mean, gold obviously has luster and looks like a metal. Silicon kind of looks like a metal. We know that this is a metalloid, and then diamond looks like a non-metal, meaning it's it's not ductile, it's not malleable, and it's a very hard material. So what properties do these materials share? Well, we know that they're all solids to start, and we know also that they have crystal structures. These are all crystalline solids, meaning that their atoms are organized into periodic lattices. So now let's talk about the electronic properties of each material. So we know that metals tend to be conductors. This is something that's unique to metals. Semiconductors or metalloids tend to have properties that are kind of a mix between metallic materials and non-metallic materials. So that's why we call them semiconductors. So these are conductors, but they only conduct well under certain conditions. And then we have nonmetals, which we know are insulators. They don't conduct electricity. So the question is where do these electrical properties come from? And why is gold a conductor, silicon a semiconductor, and diamond an insulator? So by the end of this talk, you should be able to explain that at least with the most basic concepts from Gen Chem that we use, like linear combination of atomic orbitals. So to kind of give away the answer before we even start, what you're going to find out is that a metal has what we call, well, all of these structures are going to have what we call a band structure, where we have, instead of just having single atomic orbitals, we're going to have molecular orbitals that span the entire material. And what we're going to find is the key thing here is where is the Fermi level. Now, the way to think about the Fermi level, and we're going to talk about this in more detail, is where is the gap between where the electrons are, the orbital that the electrons are in, and the orbital that the electrons aren't in. So we're going to see that depending on where that Fermi level is, whether it's inside of a band gap, or inside of a large band gap, will determine how conductive a material is. Oops, here we go. Okay, so we're going to start with something that we know, which is the LCAO-MO construction. So LCAO stands for linear combination of atomic orbitals. So what we're doing is we're taking atomic orbitals, and remember, the orbitals are just mathematical equations that describe the probability of where an electron is around that. So the 1s orbital, which is a circle, sphere, that surrounds the nucleus of the hydrogen atom, for example, that is a mathematical equation, and it's a probability equation of where electrons can be. And we can add and subtract these atomic orbital equations to give us molecular orbitals, meaning we can add the equations together and give a combined equation that will give us a bonding orbital, and we can subtract the two orbitals, giving us what we call an antibonding orbital. So when we add them, we get an overlap of the electron density, and this is called a bonding orbital. So we call this a sigma bond, and it's lower in energy because it puts electron density between the two nuclei. And then when we subtract the two orbitals, we get what's called an antibonding orbital, because now there's a node meaning no electrons in between the nuclei. So you get a lot of repulsion. We call this the antibonding orbital. And then if we have 2 electrons, those 2 electrons are going to fall down, and depending on the number of electrons, we can calculate the bond order. So if you remember, the bond order is the number of bonding electrons, basically minus the number of antibonding electrons, and then you also count the lone pairs in there, or the non-bonding electrons. So this one would have a bond order of 1 because both electrons fall into the sigma bond. Now let's look at what happens when we take two atoms like lithium and we start to bond them. And let's start to look at what happens when we take 2 atoms of lithium, 4 atoms of lithium, 8 atoms of lithium, 16 atoms of lithium. What we're doing is we're basically building up from something that we know, which is basically bonding 2 lithium atoms. We can do that with LCAO-MO, and then extending it to where we have essentially moles of atoms in the solid, right? So when you have a solid material, you don't have 2 lithium atoms. You have however many moles of lithium you have in your solid in front of you. So we're going to focus mostly on the valence electrons, because we remember that the valence electrons are what does the bonding. The core electrons are pretty much shielded by the valence electrons, so they don't really participate too much in the bonding. So that's what we're going to assume for this video, even though that's not always 100% true. So with lithium-2, we get the following, right? So our valence orbital is the 2s, and when we put 2 lithium atoms together, we get 2 electrons in the 2s bonding and no electrons in the anti-bonding. Now, here's where we're going to go a little bit beyond what we've done. So when you get 4 lithium atoms together, we can start to make these combinations, and now we have 4 atoms that we have to contend with. So if we put in 4 orbitals, we're going to get 4 orbitals out, meaning we always have to conserve the number of orbitals. So you can start to imagine how we can add and subtract these orbitals in different ways. So when we do the addition of all the orbitals, we can get this orbital that spans all 4 lithium atoms, and we get this super bonding orbital. And then if we go up a little bit in energy, we can get one where it bonds, but there's a node in between 2 of the 4 in the middle, sort of. There's a node in the middle. But it's still bonding because we still have overlap between these 2. And then when we go into the anti-bonding orbitals, we see that in this case there is some bonding in the middle, but we have 2 nodes now. So as we increase the number of nodes, you're going to see that that's going to increase our energy. And then finally we get the fully anti-bonding orbital where we have a node between every atom. We get 3 nodes. So you notice that as we go up in energy, we go up in the number of nodes, which means that there's less overlap of the orbitals. Now at this point we're going to start to, so I took the time to work this out for lithium-8. But you can see again, we basically are increasing the number of nodes as we go up in energy. And what you notice is, even though we're becoming more and more complicated, now we have 8 orbitals, we could see that they're always halfway full. So all of the bonding orbitals are occupied with electrons. All of the anti-bonding orbitals are not occupied with electrons. And what you'll notice too is that the energy spacing between the orbitals is going down. They're getting closer together. So when you do lithium-16, at this point I stopped trying to figure out all the pictures for the orbitals. But you can see the same effect is starting to happen. We're starting to condense the orbitals down, and they're getting closer together, and they're still all filled up here in the bonding area, and they're still all empty in the anti-bonding area. And then if we take it to its logical conclusion, what we get is what we call a band. So a band is where we have a whole manifold of orbitals, meaning almost an infinite number of orbitals. Or in this case, lithium infinity would be infinite. But if you had a mole of lithium, then you'd have a mole of 2s orbitals. And in this manifold, it's going to be halfway full, because in the beginning we have 2 possibilities. We have either a bonding or an anti-bonding case. And as you can see here, we have 2 electrons, so we're going to fill this orbital halfway up. With those electrons. We could have a maximum of 4 in this combination set, but we're halfway full because we started with 2 in the bonding. And what's interesting about this is we get a bonding set and an anti-bonding set, and in these sets, if you look in and we zoom in, the way we defined a band is a collection of molecular orbitals that arise from extended three-dimensional overlap in solids. So now these two s orbitals are bonding all the way across the entire structure. Basically, all the s orbitals are overlapped together and form these extended molecular orbitals that span the entire structure. So in essence, this is becoming our sea of electrons, right? So when you think of a metal and you think of metallic conductivity, many of you have this picture in your mind that there's like a sea of electrons, and the electrons can move across the whole structure. Well, what the sea of electrons is these molecular orbitals that have all come together. They're all two s orbitals that have bonded with each other. And because they're all bonded with each other, the probability distribution function for an electron begins to span the entire structure. Now, if we zoom in and we look, what we're going to get is these molecular orbitals. So each one of these little lines is a molecular orbital, but they're very, very, very close together, almost infinitesimally separated in energy. Because remember, as we increase the number of electrons, we decrease the spacing. So the energy separation between orbitals is so small that discrete energy levels form what we call a continuum. So there are energy levels, but they're so packed together that it almost is like a continuum of energy levels. And if you look, if we do this thing called X-ray determined band structure, this is I think this is XFs, which is basically an X-ray technique that measures where the electrons are in a structure. You can see that these are the energies of all of the electrons that come out, and it's not in any kind of, there's no line function where there are electrons. It's this band function where there are electrons that kind of go over a continuous band of energy, and they're occupied. And you can see that we can even assign some of these electrons to different parts of the compound. So this one is strontium titanate, and we can say, well, okay, here are the electrons from the titanium, here are the electrons from the strontium, and here are the electrons from the oxygen. This data was actually collected when I was in graduate school from one of the synchrotron radiation sources. So now let's talk a little bit about what defines a band. So a bandwidth is the range of energy that the molecular orbitals extend. So you can see that the bandwidth here is from about 9 to about 3 eV, which is, remember, that's electron volts, or a measure of energy. So the bandwidth, or how big this band is in energy space, is determined by the effectiveness of the orbital overlap. So if you get really good overlap, you're going to get a very wide band. If you get very poor overlap, you're going to get a very narrow band, because you can kind of think that fewer states are going to be in that band. So the bandwidth, or the thickness of the band in energy, is determined by how well the orbitals overlap. So for example, if you take d orbitals and you try to overlap them, they don't overlap as well as s orbitals. And that kind of makes sense, because if you think of an s orbital, that's a sphere and it can just overlap with another sphere. D orbitals are those balloon-like structures that have 4 balloons held together. They can only overlap where the balloons touch. So the D band is going to be narrower than the S band, and that's because of the overlap. So now let's look at what happens when we have a little bit more complex structure. So if you look at silicon, and we remember back to the days of doing hybridization, silicon has some p orbitals and it has some s orbitals, right? And when it forms bonds, we know that the s and p orbitals will overlap and form what we call sp hybrids. The same thing happens in solids. So these orbitals will overlap and we form an sp valence band and an sp conduction band. So basically the way to think of this is these are all of the bonding orbitals down here, and these are all of the anti-bonding orbitals up here. And we call this, this low energy one that's bonding, the valence band, and we call this one that's not bonding, the conduction band. It's just vocabulary to define bonding versus anti-bonding. We'll see in a little bit that the reason why this is called the conduction band is because this is the area where electrons can move around when you want to conduct electrons. So what you notice, though, is that just like we have a gap between the S and P, we also have a gap between the sp valence band and the sp conduction band. This energy separation is called the band gap. So now we have to define one more term, and that's called the Fermi level. So I don't remember in class if we introduced this concept of the highest occupied molecular orbital and the lowest unoccupied molecular orbital. But if you look, basically the HOMO, or the highest occupied molecular orbital, is going to be the orbital that has electrons in it. And then the LUMO is the orbital that does not have electrons, meaning it's the first orbital that doesn't have electrons. So the gap between the occupied orbital and the unoccupied orbital, in the middle of that gap is going to be where we call the Fermi level. It's just a line that we put that tells us that this is the separation between places that have electrons and places that don't. So in the case of a partially filled band, where we have, like this would be the 2s band of the lithium, the Fermi level lives inside of the band, meaning the band is only half full. So in this continuum of states, we have infinitesimally close states that are empty and infinitesimally close states that are full. Now, in the case of a band gap, when you have a band gap, the Fermi level, or where the gap between the occupied molecular orbital and the unoccupied molecular orbital, that'll be in the middle of the gap. And this is going to be important for conduction. So the key thing to understand with conduction is that conduction occurs by the transfer of electrons between partially occupied orbitals near the Fermi level. So what do I mean by that? We're going to simplify this. So in a metal, it turns out that if you look, because these orbitals are so close together, we get what we call a distribution of states around the Fermi level. So what does that mean? Because I have a kind of a graphic of this. So at 0 Kelvin, meaning you have no temperature, no energy at all of the electrons would be sitting happily in their orbitals and they wouldn't be able to move around. They'd be locked in. But if you give this some temperature, some energy, and if these gaps are really, really small, meaning if the gaps are small and on the order of that energy, so let's say that these gaps, if you take just the thermal energy of the temperature of room temperature, if that energy is enough, then we can promote an electron, just like we can promote an electron with light energy, meaning we can cause an electron to go from a low energy state to a high energy state with light. We can do the same thing with heat, if the gap between the states is small enough. So when we get up to room temperature, what happens is some of these electrons get promoted to higher states. And then here we get these states that are sort of partially occupied, because some of the electrons have been promoted up into higher states. So now we have a bunch of states with just one electron in them. And then if you have that, and these states are delocalized over the entire structure, meaning we have a molecular orbital that goes from one area to another, if we put an electron in, this electron can start to hop from unoccupied state to unoccupied state, and then it can go across the structure all the way to the other side. So what happens with conduction is, the two requirements for conduction is that you need a Fermi level to be in the middle of a band, and you need some temperature to get the electrons to be promoted so that you have some holes to put an electron in. And then once you can get an electron in from the outside, because these molecular orbitals are delocalized over the entire structure, the electron can go flying through the material very easily and out. And then this is how conduction happens. So this is sort of the sea of electrons. These electrons that are sitting in the middle of the band that are promoted and individually occupied, when you put an electron in, it can be delocalized over the entire structure and make it all the way through very quickly. So this is why gold and other metals are conductors. So just to give you a sense for this particular slide goes a little bit beyond what the textbook does, but just hear me out and take a look at this because it's interesting. So with transition metals like copper, it makes perfect sense, because if you look, we're going to have an S band. That's going to be totally full with copper. It's 4s2. So those two electrons are going to completely fill up the S band. But then with the D band, we're going to have something like 3d9. So we're going to have 9 of the 10 electrons full. So this band is going to be 9/10 full. And then right here at this Fermi level, if we're at room temperature, we can promote some electrons and get the conduction of electrons through the material. So that makes sense. But here's the problem. What about magnesium? Magnesium is a metal and it's conductive. But if you look, the 4s electrons would completely occupy the S band. So we shouldn't have any conduction here, because if a band is totally full, there's nowhere to put electrons in. It doesn't work. So what happens? How does this actually conduct? So we have to remember that when we have a magnesium atom, it not only has access to the 4s, but it also has access to the 4p. And these 4p orbitals are open and available to do things, to do chemistry. So it turns out that metals to the left of the periodic table experience what we call sp overlap. Basically, the s and p orbitals hybridize, and we get these two overlapping bands. We get the s band and the p band. And because they overlap, some of the electron density can spill over into the p band, and we give a little bit of electron density to those p orbitals, and now we get two partially filled bands that can conduct electrons. So this is what happens when we have metals that seemingly shouldn't be able to conduct because their s band is totally full. The reason why it works is because of hybridization with the p orbitals, and then we can get conduction because we have partially filled bands. Okay, so now let's just take a quick look at semiconductors, because these are really interesting. These actually have the potential to solve part of the energy problem, because these are what are used to make solar cells. So like I said, with semiconductors, we have a band gap. So we have an sp valence band, and this totally full with these 4 electrons. So all 4 of the electrons go into the sp valence band. And then we have a totally empty band where we have the conduction band. Now, just like with any other molecule, if we give this enough light energy, meaning we put a photon in here, or if we give this enough heat energy, enough energy that we can kick electrons up here, either way, if we can kick electrons up here, we can get electrons into the conduction band, and then we would have a partially full band. So if you look at the energy difference, it's 1.16 eV, which is a little bit more than room temperature. So it's a good amount more than room temperature. You'd have to heat this up quite a bit. But this is definitely in the range of light. And so if you give this a little bit of energy and you promote some electrons with light, meaning in the light, if there's enough light energy, meaning you shine light on it with enough energy to promote electrons, now you can get conduction because some of the electrons are promoted into this band, and now you have a partially filled band and a partially filled band. That's why this is called the conduction band, because this is where you can start to get the electron hopping through the material. So if you look at the conductivity as a function of temperature, when you heat these, so at room temperature the conductivity is pretty low. 273 is right over here. But if you heat these things up to like 500 Kelvin, you start to get much more conductivity because you start to populate the conduction band with electrons. And we can actually play some games. So this goes a little bit beyond what the textbook does, but not that much. The textbook does talk about doped semiconductors. So there are 2 ways that we can play games with these semiconductors. One is we can basically dope electrons into the valence band, or the other is we can pull electrons out of, we can dope electrons into the conduction band or pull electrons out of the valence band. So in the case of an N-type semiconductor, the reason why we call it N is because it's a negative type semiconductor. So we put in some phosphorus into our semiconductor, and those phosphorus atoms kind of sit here, right below the valence band. And these are real close to that, we put them right underneath the conduction band. And these are real close to the conduction band. So it's easy for us to promote electrons into the conduction band from these dopant levels. Or the other thing we could do is we can make a p-type semiconductor where we put in some gallium, which has one fewer electron than silicon, and now we can promote with just thermal energy electrons up into these dopant sites. Either way, the net effect is that we get a partially unfilled band and we get more conduction. So this is why we call them N-type and P-type semiconductors. Okay, so now with insulators, we have some bands. Don't worry about this A1, T2, T2, A1. These are just basically different types of bonding and antibonding orbitals. But with insulators, this gap is not anything close to the energy of light, right? So this is a huge band gap. 5.5 EVs would be something in the high X-ray range or something like that. So most thermal or optical sources wouldn't be enough energy to kick an electron up into the conduction band. So these things will never conduct light unless you hit it with some kind of really super high energy radiation. And you'll never get a partially unfilled band. So that's why they're insulators. So semiconductors will conduct, but they'll conduct only with help, light or heat. Insulators will never conduct because they are just, the band gap is too big. So if you look, silicon is 1.16 eV, and that equates to about 1,000 nanometers. So this is in the infrared area. So you just need infrared light to get this thing to go. Diamond, on the other hand, well, I guess I misspoke. So diamond, on the other hand, this is 225 nanometers, which is in the UV. So you would need higher than UV radiation in order to get this thing to have enough energy to go up. It wouldn't be X-rays. So now we understand the difference. Gold, the reason why it's a conductor is because the Fermi level lies in the middle of a band. A silicon is a semiconductor because the Fermi level lies in a relatively short or small band gap. And diamond is an insulator because the Fermi level lies in between a very large band gap. So I just want to give you guys one example of why this is important. So a lot of you guys have TVs, and TV technology is based on LEDs. And now actually it's liquid crystal displays, and they even have quantum dot LEDs now. So a lot of the stuff that I worked on in grad school is winding up in TV technology right now. So LEDs are really cool because they generate a lot of light with a relatively small amount of power. And you can tune their color to give you different colors, like this is a blue, a green, and a red LED. So they require much less power than filament bulbs to achieve the same light output. That's why a lot of places are changing their bulbs to LED bulbs, because you can save a lot on cost, and it's better for the environment. They also are much more efficient in terms of operational lifetime, so LEDs can last a lot longer. And what we're going to find out is that the color of the light can be tuned by changing the properties of the materials that you use to make them. So the way this basically works is we have to go back to our understanding of the N-type and the P-type. So the N-type is doped to have these states that are below the conduction band and they have electrons in them. And the P-type is doped to have empty states right above the valence band. So to make an LED, what we do is we mush these two together. And we take a N-type and a P-type and we stick them together physically and connect them. And then what happens is, because the Fermi level has to equalize, we get this continuous bending of the band across the material. So this is the junction region where we're going from N to P, and the junction region has this continuous sort of transition from the P to N. So now the way an LED works is as follows. So what we do with an LED is we apply a bias against it. So we hook this thing up so that there's a minus charge on the N-type and a plus charge on the P-type. And then what happens is we have a carrier that starts to get pushed toward the positive conduction band. So because we're applying a field across, the electron's going to want to go toward the positive, and so it does. And then when it reaches the depletion region, it can fall down to the valence band and release a photon. And this is the photon of light that we can capture to, this is the photon of light that makes the LED look like a light source, meaning this is where it gives off the light to be the light source. So the key thing, the cool thing about these things is, because we have this intrinsic field in between, we're using the properties of the material to our advantage. So if we can tune the gap between the conduction band and the valence band, or if we can tune our band gap, we can get LEDs of different color, because the energy at which it falls will be different and a different color. So you can imagine if we have a large band gap, we might be in the blue side of the spectrum. If we have a smaller band gap, we might be on the red side of the spectrum. So that's how you go about designing LEDs. You have to design materials that have band gaps in the color region that you want to have for your emitter.